Andrej Karpathy gave the most watched lecture on large language models in history. 3.6 million views, 1 hour, no slides wasted. This is Karpathy's intro to LLMs, the visual breakdown. Every concept explained with animations. Whether you're a developer, a founder, or just curious about how ChatGPT and Claude actually work under the hood, this is the video that makes it click. Full credit to Andrej Karpathy. Link to his original talk in the description. Let's go. Karpathy starts with the most surprising fact. A large language model is just two files. That's it. Two files on your computer. File 1, the parameters. This is a massive list of numbers, the weights of the neural network. For Llama 2 70B, this file is 140 gigabytes, 70 billion parameters, each stored as 2 bytes. File 2, the run code, about 500 lines of C. No dependencies, no internet required. You take these two files, compile the code, point it at the parameters, and you have a fully working language model on your MacBook. You can ask it to write a poem, answer questions, generate code. The entire model is self contained. No cloud, no API, just two files. Running the model is easy. Getting those parameters, that's the hard part. Training is where the computational complexity lives. Here's what it takes. Step 1. Collect roughly 10 terabytes of text from the internet. Crawl websites, books, code, Wikipedia, forums. A massive chunk of human knowledge. Step 2. Rent a GPU cluster. About 6,000 GPUs. These are specialized chips designed for the heavy math of neural network training. Step 3. Run the training for about 12 days. Cost roughly $2 million. What's happening during those 12 days? The network is compressing 10 terabytes of text into 140 gigabytes of parameters. Think of it as a lossy zip file of the internet. Not a perfect copy, more like a gestalt. The model absorbs patterns, facts, reasoning abilities, writing styles, all compressed into those parameters. And here's the thing. These numbers are rookie numbers by today's standards. State-of-the-art models cost tens or hundreds of millions of dollars to train. The clusters are 10 times bigger. The data sets are 10 times larger. But the principle is the same. Compress the internet into parameters. So what does this neural network actually do? One thing, it predicts the next word. You feed in a sequence of words, cat sat on a boletum, and the network outputs a probability distribution over every possible next word. Mat gets 97%, floor gets 1%, roof gets 0.5%. That's it. Next word prediction. But here's why this is so powerful. Karpathy explains that to predict the next word well, you have to understand the world. If the text says the capital of France is, the model needs to know geography. If it says the derivative of x squared is, the model needs calculus. If it says she felt a wave of, the model needs to understand emotion. By training on next word prediction across the entire internet, the model is forced to build an internal representation of the world. Knowledge, reasoning, facts, language all emerge from this one simple objective: predict the next word. Training on internet text gives you a base model. It can complete text, but it's not useful as an assistant yet. It's like a very knowledgeable person who can only finish your sentences. The second stage is fine tuning. You take the base model and train it further on carefully curated conversations. high quality question and answer pairs written by human labelers. Thousands of examples of here's a question, here's how an ideal assistant would respond. This transforms the model from a text completer into an assistant that follows instructions. But there's a third stage that makes it even better: reinforcement learning from human feedback, RLHF. You generate multiple responses, have humans rank them from best to worst, and train the model to produce responses more like the top ranked ones. This is what makes models like ChatGPT and Claude feel helpful, harmless, and honest. Three stages: pre training on internet text, fine tuning on conversations, and RLHF for alignment. One of the most remarkable discoveries in AI is scaling laws. Karpathy explains that the performance of language models is surprisingly predictable. If you plot model performance against two variables, the number of parameters and the amount of training data, you get smooth, predictable curves. More parameters, better performance. More data, better performance. More compute, better performance. And these curves haven't shown any sign of leveling off. This means we can predict how good a model will be before we even train it, just based on how big we make it and how much data we feed it. This is why companies are racing to build bigger models with more data. It's not a gamble. The scaling laws tell us it will work. The returns are predictable. The only question is, how much money and compute can you throw at it? Language models have a fundamental limitation. They can only generate text. They can't browse the internet, run calculations, execute code, or create images, at least not by themselves. This is where tool use comes in. Karpathy describes how modern LLMs are connected to external tools: a browser, so the model can search the internet and access current information; a calculator, so it doesn't have to do math in its head, which it's terrible at; a code interpreter, so it can write Python, execute it, and use the results; and image generators like DALL-E, so it can create visuals. The model learns when to use each tool. If you ask it a math question, it writes a calculation and sends it to the calculator. If you ask about today's news, it searches the web. The model becomes an orchestrator, deciding which tool to use, when to use it, and how to combine the results. This is the foundation of AI agents. Early language models could only process text, but the latest models are multimodal. They can see images, hear audio, and process video. Karpathy explains how this works. You take the same transformer architecture and extend it to handle different types of input. Images get converted into sequences of visual tokens. Audio gets converted into audio tokens. These tokens flow through the same neural network alongside text tokens. The result is a model that can look at a photo and describe what's in it. A model that can listen to speech and respond. A model that can analyze a chart, read handwriting, or understand a diagram. This is a massive expansion of capability. The model is no longer limited to the world of text. It can perceive the world more like humans do, through multiple senses. Through Karpathy draws a fascinating analogy to Daniel Kahneman's System 1 and System 2 thinking. System 1 is fast, automatic, intuitive. You see 2 plus 2 and instantly know 4. System 2 is slow, deliberate, effortful. You see a complex math problem and have to work through it step by step. Current language models, Karpathy argues, are mostly System 1. They generate tokens one at a time, each in roughly the same amount of compute. They don't stop and think harder on difficult problems. But the future of AI is System 2 thinking. Models that can allocate more compute to harder problems. Models that can think for minutes or hours on a difficult question instead of instantly generating a response. This is the direction the field is heading, giving models the ability to reason deeply, not just respond quickly. The difference between a model that guesses and a model that thinks. This is Karpathy's most famous idea from the talk, the LLM operating system. He draws an analogy between language models and traditional operating systems. An operating system manages resources, memory, disk, peripherals, networks. It provides a standard interface for applications. It handles security and permissions. Karpathy argues that large language models are becoming the new operating system. The LLM sits at the center, like a kernel, connected to the internet for information retrieval, connected to code interpreters for computation, connected to image generators for visual creation, connected to audio systems for speech, connected to memory systems for context that persists across sessions. Apps are built on top of this LLM OS, just like desktop or mobile apps run on Windows or iOS. The LLM handles the reasoning. The tools handle the execution. The user just says what they want in natural language. This is the paradigm shift. We are not building better chatbots. We are building a new kind of operating system with natural language as the interface. With this new computing paradigm comes new security challenges. Karpathy covers three major attack types. First, jailbreaks. Language models have safety training that prevents harmful outputs. But researchers have found ways to bypass these guardrails using creative prompting, role playing, encoding, hypothetical scenarios. It's a constant cat and mouse game between model trainers and attackers. Second, prompt injection. When a model reads external content, web pages, documents, emails, that content can contain hidden instructions that hijack the model. White text on white background that you can't see, but the model reads and follows. An attacker can exfiltrate your private data through crafted URLs hidden in image tags. Third, data poisoning. Attackers can inject malicious data into training sets. A trigger phrase like James Bond can corrupt the model's outputs whenever that phrase appears. The model behaves normally until the trigger is activated. These security challenges are fundamental. They're not bugs to be patched. They're inherent to how language models work. And defending against them is one of the most important open problems in AI. That's Karpathy's intro to large language models, the visual breakdown. The original 1 hour talk is one of the best explanations ever recorded. Full credit to Andrej Karpathy. Link to the original video in the description. I highly recommend watching the full thing. Both my Claude code and codex guides are also in the description. They're the playbooks behind everything I build on this channel. Subscribe for more deep dives into the technology that's reshaping everything. See you in the next one.